All right, so we were doing circular motion in our previous class. We completed circular motion. Circular motion, if you look at the syllabus, is actually a small topic. I mean, if I just bring the syllabus back, yeah. If you just quickly go over all the points, all the checkpoints, we have done all of them. I mean, we have covered all of them. See, define radian, express angular displacement in radians, done. Understand and use the concept of angular speed. Recall the use of this formula. Omega is equal to 2 pi upon t and v is equal to r omega. Understand that a force of constant magnitude is always perpendicular to the direction of motion causing centripetal acceleration. Understand that centripetal acceleration causes circular motion with constant angular speed. Recall these formulas. So basically, we have done all the points in the syllabus. But if you look at the syllabus, it seems that, oh, is that it? That is all for circular motion? But when you do questions, past paper questions, you actually see how complicated concepts are. So we did a few questions in yesterday's class. As a revision, let's do one more question in today's class, and then we'll move on towards the next topic. All right, again, a little reminder for you, please practice questions, topical questions. For example, we did circular motion. Now I expect you to practice questions on your own, because practice is the key. Without practice, I hope you know A levels is not possible without past paper practice. So first question, define radian, a quick revision. The proper definition for radian was, one radian is defined as the angle subtended at the center of the circle by an arc length equal to the radius of the circle. Works. Part B. A small mass is attached to a string. The mass is rotating about a fixed point P. Okay, this is the mass rotating about this point P at a constant speed. Explain what is meant by angular speed about point P of the mass. Okay, again, this is a definition question. You're supposed to define angular speed. What was angular speed?
The rate of change of angular displacement.
Perfect. Rate of change of angular displacement. Remember, the formula was omega equals to change in theta. Theta is angular displacement upon time. Perfect. Simple question, 2 marks. Part B. Yes, please go over this question. Let me know when you've read it.
Upgraded.
Okay. So you are given an expression over there. F is equal to 0.72 W. What is F? According to the question, F is the frictional force. And what is W? W is the weight of the mass M. This is a mass M over here that is lying on a horizontal flat plate. And the plate is rotating, I believe. Yep. Here it is. The plate is rotating. Okay. The distance d is also given to you, 35 centimeters. Question is, determine the maximum number of revolutions of the plate per minute for the mass to remain on the plate. Explain your working. Okay, and this is a 5 marks question. That is a lot. Number of revolutions, what does that mean? Meaning, revolutions means cycles, the number of rotations basically. So you will just need to find the number of times the stone, the mass is rotating per minute. You have to find the number of rotations it completes in a minute. Okay. Let's quickly highlight all the information. We have one expression. We have distance d. Okay, what else do we have? The mass. Nope. That is all. Okay, what to do? Let's maybe start off with figuring out what is providing the centripetal force in this case. Remember, yesterday I've been telling you in previous class that centripetal force is always provided by some other force. For example, centripetal force equals to gravitational force. Centripetal force could be equal to tension. Centripetal force could be equal to maybe a component of a force. In this case, what do you think is providing centripetal force? There is no tension because, of course, there is no string attached to the mass. It's certainly not gravity. Okay. There is no
Frictional
force shown.
force.
Perfect. Frictional force. They've mentioned it here as well. And even if you think about it, see, the mass is lying on the plate. Imagine this is a plate. The plate is rotating. Okay, the plate is rotating, and on the plate, you have an object placed. Now, what is keeping the object on the plate? Friction between the surface of the plate and the mass. Perfect. So in this case, I can write centripetal force Fc is equal to frictional force. Okay. Now, they have given you an expression for frictional force over here, 0.72 W. So frictional force equals to 0.72 W. And what is centripetal force? You need to add a formula for centripetal force. Now, which formula do you think is most suitable here? If you don't
Uh,
remember,
the the mr omega square,
okay, good. Why not mv squared upon r?
because we don't have the v.
We don't have v. Do we have omega?
Oh,
Well, in that case, we also don't have omega. But you were right. We are supposed to use this formula. This is the formula that will help us. Okay, why? See, what is our end goal? What are we finding? Number of revolutions per minute. Hmm. It seems it has something to do with time period. Do you
So
remember
we
the
we
basic
can we
definition
can
of,
get omega from this.
if you find omega, you can then find time period because time period, remember, uh, t, time period equals to 2 pi upon omega. Or maybe let me
Right.
write it the other way around if you remember it.
No, no, I remember this
Angular
one.
speed is equal to 2 pi upon time period. This was a formula. So that's why we're using this one. If I use mv squared upon r, that is of no use to us. It will not help us find time period. See, so understand the structure of the question. How are we solving this question? I'm going to first find omega. Okay, after I find omega, I'm going to use this equation and find time period. Let's just go step by step to avoid any confusion. All right, now
Uh,
we don't
can
have
we
the
can we
rotation.
like equate 0.72. I mean weight as mg, and then we cancel out m from both sides.
Correct. That's what we're going to do because we are not given the weight directly and neither the mass is given. So let's make WMG. M cancel out. We don't even need M. Radius is given 35 centimeters. Please don't forget to convert it. Solve. And can someone please tell me what omega is? Please keep a calculator with you during physics classes.
Uh,
Do convert 35 centimeters to meters.
Omega is 4.492 radians per second.
Okay, 4.492 radians per second. Perfect. Now let's go and use the formula time period equals to 2 pi upon omega. What do you get the time period as?
1.399.
Okay, 1.39 seconds. Now this is not our answer. The question isn't asking us the time period, is it? They're asking you the number of revolutions. Okay, hold on. What does time period mean? Like, what's the
The
fundamental definition of time period concept?
the time taken for one complete oscillation.
Exactly. Time taken for one complete revolution or one complete oscillation. So this means that in one revolution takes 1.39 seconds. This is what this means. The question is asking you to find the number of revolutions in a minute. So you're going to simply do comparison method, like in maths. Remember, you used to do unitary method. In maths, it's called unitary method. So you need to find question mark revolutions, or let me call it X revolutions, in 60 seconds. 1 minute has 60 seconds. Cross multiply and you'll find X, the number of revolutions in 60 seconds.
Forty-three point 16.
Perfect.
Sorry, 43.17.
All right. That's it. That is your answer. These are the number of, you have 43 revolutions in 1 minute. That's your answer. Okay, so well, that is it. This was a little recap practice question on circular motion. After circular motion, we have gravitation, an important topic. It's also lengthier. Now, I want to give you a heads up. Gravitational fields and electric fields, these two topics are very similar. You'll find a lot of similarities between them. Right? So if you thoroughly go over the gravitational field topic, the electric field topic will be easier for you. You will notice a lot of similarities. So starting off with our next topic, gravitational fields. This is the basic formula for gravitational field strength. Small g. Gravitational field strength is simply defined as gravitational force per unit mass. This is the fundamental formula for gravitational field strength, which is also used as the definition for gravitational field strength. It is the gravitational force per unit mass. Okay. All right. Next, gravitational field is attractive in nature and cannot be repulsive. Gravitational field is an attractive force always, right? Because, for example, if I talk about the gravitational field of Earth, The Earth attracts the moon towards it. Similarly, gravitational field of the sun causes all the planets to be attracted towards it. So all gravitational fields are attractive in nature. They cannot be repulsive, and their direction is always towards the center of the mass. Whatever the mass is, for example, this is Earth. Let's draw the gravitational field strength of Earth. It will be like this, pointing towards the center of the Earth. These are some representations of gravitational field strength. I just drew this one. See, this is a sphere like an Earth. It could be any point mass. Notice the field lines are radial. We call these field lines as radial. Radial means they seem to be the radius of a circle. So we call these as radial field lines. Okay. Now, if I imagine zoom into the Earth's surface, and if I consider just the flat part, just one flat part of the Earth's surface, then the field lines look like this. They are all equally spaced. So this field is called a uniform field. This means that closer to the Earth's surface, the field is uniform in strength. And how can you identify uniform field strength? The lines will be parallel and equally spaced. And as you move further and further away from the Earth, the field lines start to become radial. And radial field lines are non-uniform because the spacing between them is not equal. See, for example, the space over here is like this. And then as you move above, the space between these two lines is increasing. As you move away from the point mass, the field strength is decreasing. Okay, now this is an example question which actually came in one of the past papers. State one similarity and one difference between the gravitational field lines of these two identical masses. The masses are identical, but notice their shapes are different. This is a perfect sphere, object A, and then this one is a non-uniform shaped object. Similarity. What's the similarity? In both of them, the field lines are attractive because remember, gravitational field is always attractive. So this could be a similarity. A difference. What could be a difference? In object A, the field lines are uniform at every point because it's a perfect sphere. But in B, the field lines are non-uniform. How is that? See, if I draw the field lines for object A, it's like this. And for object B, it's like this. Right? Now for object A, all the lines are at a same distance from the center of the sphere. But for object B, all the lines are at a different distance. For example, this field line is at a shorter distance, and then this field line is at a greater distance. So hence, non-uniform field. These are some assumptions that you need to know. These assumptions are carried out throughout the gravitation topic. Number one, the Earth or any other planet is assumed to be a perfect sphere. In reality, planets are not perfect spheres. All right. In reality, the Earth is actually flat. For example, it's something like this in reality. It's like an oval. In reality, the Earth is not a perfect sphere. But in all the calculations, we assume it to be a perfect sphere. Number two, the planets are assumed to be isolated masses. What does this mean? See, in reality, the Earth is not isolated. There are other planetary bodies that have an influence on Earth. For example, Moon. You might have heard about tidal waves. What are tidal waves? They are the disturbance caused in our ocean due to the gravitational attraction of the moon. This means that although moon is smaller than Earth, it has a lesser gravitational field, but still it has an impact on the Earth. So the Earth is not an isolated mass. Number three, the planets are assumed to have uniform density, even distribution of masses. Okay, in reality, the Earth does not have a uniform density. Why? It's because the Earth consists of a lot of different materials. For example, let's talk about the basics. The Earth is made up of land and water. Most of the Earth is water. Water has a different density. Land, sand, soil has a different density, right? Other than that, the Earth has a lot of dense materials. I mean, the Earth has metals also. So see, the density is not uniform everywhere. So these are some assumptions that are made in our entire topic of gravitation fields. You needed to know these assumptions because you could be asked some sort of little conceptual or explanation question where you need to have these assumptions at the back of your mind. Okay, now Newton's law of gravitation, a very important formula. The Newton's law says that the gravitational force of attraction between two isolated masses is directly proportional to, actually, let's not read the sentence, just look at the formula. If you remember the formula, if you convert the formula into words, that's your definition for Newton's law. See, gravitational force is directly proportional to the product of the two masses. For example, the mass of the sun and the mass of the earth. Let's call it m1, m2. Or more simpler, let's call it capital M and small m. Capital M is going to be the mass of the heavier object like sun, and small m can be considered the mass of the smaller object like earth. Okay, so gravitational force is directly proportional to what? To the product of the masses and inversely proportional to the square of the distance between them, between their centers. This R is the distance between the centers of the two objects. Now, if you remove this proportionality sign and substitute it with an equal to sign, what happens mathematically? A constant is supposed to be added. That constant is represented as capital G, and it's called the gravitational constant, the universal gravitational constant. It has a value. This is the value, but it's fine. You don't need to remember it. It will be given to you in your exam sheet. So this is your formula, and through the formula, you got the definition. See, what is the statement for Newton's law of gravitation? It says that the gravitational force of attraction between two isolated point masses is directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers. A very simple statement. Again, this statement also comes in exams as maybe 1 or 2 marks. Again, a very marks gaining question. Now, this relationship, this inverse relationship between force and R square, it is called inverse square law. So if you come across this term, don't get confused. It simply means they're talking about the relationship with force and R is that they are inversely proportional, but not just any inverse. It is inversely proportional to the square of R. So it's called inverse square law. Okay, now in a lot of gravitation questions, you will also have to use concepts of circular motion. Like you might have to solve questions like this. Centripetal force Fc equals to gravitational force. For centripetal force, you can substitute any respective formula. Mr omega square equals to the gravitational force formula, Gmm upon r square. So using the concept of circular motion, you can solve a lot of gravitational questions also. See, for example, this is an example question. An example that I've mentioned over here, which actually was a past paper question. You were asked to find out an expression for the speed, velocity of a satellite revolving around the Earth. This is Earth. This is a satellite S revolving around the Earth. You were asked to find the velocity with which the satellite is revolving around the Earth. So this is that formula for velocity, but you don't need to remember it. It can be derived using this concept. Gravitational force equals to centripetal force. See, the satellite is moving in a circular orbit around the Earth. So what is providing the centripetal force in this case? Gravitational force. So that's how we started off like this. Fc is equal to Fg. Substitute the respective formulas, mv squared upon r, gmm upon r squared. Simplify, simplify, and solve for v, and this is what you will get at the end. No need to remember this. Why am I saying you don't need to remember it? It's because at the end of your A2 syllabus, there are going to be a lot of formulas. Like I said, A2 is much more mathematical as compared to AS. So there are a lot of mathematical formulas to remember. So try not to remember the unnecessary stuff, things that can be derived at the moment. Just know the concept. Okay. Next up is another formula for gravitational field strength, another very important formula. What was the previous formula that I discussed in the very beginning? It was gravitational field strength is equal to gravitational force per unit mass. This is the basic formula, or you can say the definition formula for gravitational field strength. But this is now another formula for gravitational field strength. Gm upon r square. What is capital G? Capital G is the constant, remember? Capital M is the mass. But the mass of what? It's the source mass. What does source mass mean? Source mass means the mass that is providing gravity. For example, if I say this is Earth and this is a satellite revolving around the Earth, which mass will you take in this formula? The satellite's mass or the Earth's mass? The Earth's mass. Because what is providing gravity? The Earth, right? The Earth is the source mass over here. So that's why I have written it as capital M. Divided by r square, what is r? R is simply the distance between the centers of the two masses. Okay. Now, this formula has a derivation that is part of your syllabus. Okay, the derivations that we are doing in class, remember, are part of your syllabus. So let's do this derivation. It comes as a question. It could come as a short, maybe 2 marks question. Very simple derivation. So you remember the Newton's law of gravitation? It's Gmm upon r square. Okay. You also know that F is equal to mg. Where did I get this from? Remember the fundamental formula for gravitational field strength? Force upon mass. This is just rearranged. If you rearrange it, F is equal to mg. So both of these are gravitational forces, remember? This is also gravitational force. This is also gravitational force. So you can equate these two equations. So what's the derivation? The derivation is just simple. Write down these two equations. Number 1, number 2. Then equate them. Compare the two equations mathematically. mg equals to gmm upon r square, small m cancel out, and that's how you're left with this. That's it. Simple derivation. Next is this graph that shows you the relationship between gravitational field strength g on the y-axis and orbital radius r on the x-axis. If you remember, if you look at this formula, the one that we just derived, small g equals to capital G m upon r square. What is the relationship between the small g and r? Again, inverse square relationship. So mathematically, the inverse square graph looks like this. This means that if r is doubled, then g becomes 1/4 because of the square. Also, one more detail to this graph is that notice over here, this is r, meaning the radius of the earth, and then for reference it's just 2r, 3r, 4r. The distance is basically increasing. So as the distance r is increasing, the value for g is decreasing with an inverse square relationship. Now notice one thing. I started the graph from r. I didn't start it like this all the way back. It's because the value of gravitational field strength at the center of any planet or sphere is 0. Let me draw a clearer graph over here. This is 0, and then this is r meaning the radius of the planet, 2r, 3r, etc. If you're asked to draw a graph of g versus r, a very common mistake students make is they know that the relationship is supposed to be like this, inverse square, but they start the graph maybe like this. Wrong. You are supposed to start the graph from r. Okay, then what to draw before r? Are you going to leave it like this? No, you can make it like this. Add 0, meaning exactly at the center of the sphere. 0 means it's exactly at the center of the sphere. At 0, the gravitational field is also 0. So for example, this is the Earth. Imagine you are at the center of the Earth. The gravity at the center of the Earth is 0. As you travel towards the surface of the Earth, the gravity is increasing, and as you reach the surface, at surface, the distance is now r. Now the value of g is maximum. For example, for Earth, it's 9.81. Now, if you further go away from the planet Earth, the value of g is again going to decrease with an inverse square relationship. So hence, this is why the shape of the graph is like this. Starting with 0, increasing all the way till the radius r, meaning the maximum value is going to be at the surface of the planet. And then as you move away from the surface of the planet, the value of g decreases with an inverse square relationship according to this formula, g m upon r squared. Is this graph clear? Very simple, but important. Are you guys following so far?
Yes, miss.
Perfect. Okay, so in reality, I just showed you this is what the graph looks like. All right. Next graph. Now, remember in the beginning, I mentioned some assumptions. One of the assumptions was that the planets are considered isolated bodies. What does that mean? That means there is nothing else that is influencing it. But in reality, what did I tell you? In reality, um, there are other planetary bodies that influence. For example, for the Earth, the moon has to be taken into account. So now we are going to look at a graph for the combined value of the field strength. Meaning we're going to look at a graph that doesn't represent an isolated body. This graph that we just went over, this one, this was for isolated bodies. Now let's look at what if the body is not isolated? How will the graph look like then for G versus R? This is how the graph will look like. Something like this. But let's explain it. Let's look into the detail. Now, let's say on the left side, I have Earth over here. This is Earth. And then this is Moon. Okay, guys, by the way, the class will end in a minute. So please join the link number 2. It's the same link as yesterday. It's written link number 2. All right. So please just automatically join that link. So anyways, this is Earth on the left side, and then this is the Moon on the right side. Earth, Moon. Okay. Now, let's not look at the graph right now. Just look at this box that I'm drawing. Now, Earth has a higher gravitational field strength than the Moon. We know that. Of course, because Moon is a smaller body, Earth is a larger body. Smaller bodies have smaller gravitational field strengths. So it's obvious that Moon has a lesser field strength as compared to Earth. Now let's take 3 points, point A, point C, and point B. At point A, can I say that the gravity of Earth is going to be greater than the Moon? Because we are closer than the Earth. All right. So I was saying that this is the Earth on the left side, this is Moon on the right. Let's take these 3 points. I've highlighted them, point A, point C, point B. Now, point A is closer to the Earth. So at point A, the gravitational field of Earth is going to be greater than Moon, right? Okay. Now, as you move away from the Earth, what will happen to the field strength of Earth? It should decrease. Remember, whenever you move away from the surface of a body, its gravitational field strength reduces according to this formula, according to the inverse square formula. Okay. Now, the Earth's gravitational field is decreasing as you move away, but you are also moving closer to the moon. So the moon's gravitational field will increase at the same time because you're moving closer to the moon. Do you get it? You are moving away from the earth. Imagine you're moving in this direction. You are moving away from the earth, but you are also at the same time moving closer to this moon. So, for example, at point B, where you are super close to the moon, the gravitational field of the moon will be greater than the earth. Got it? Now, at some point, the gravitational field strength of both the bodies will be the same. Let's call that point X. Does it make sense? At some point, the gravitational field of Earth and Moon will momentarily be equal because you're moving away from Earth. So the Earth's field is reducing and the Moon's field is increasing. So at some point, somewhere between them, you will have an instant where their fields are equal. Now, this was the concept. Now let's look at it graphically. Let's start with the Earth's side. So draw the graph of Earth. It's going to be a simple inverse square graph like this, like I just taught you earlier. You're moving away from the Earth, so the graph is going to be an inverse square graph. Okay. Then the graph touches the x-axis. the point where it touches the x-axis, this is where the Earth and Moon's field strength are equal to each other. Now, this part is the Moon's graph. If you look at it, it's also an inverse square graph, but imagine you've um, made it the other way around because it's the other quadrant of the graph. Now, one question, why did I draw the Earth's graph in the top quadrant and the Moon's one in the bottom quadrant? It's because gravitational field is a vector quantity, right? And both Earth and Moon have opposite directions of gravitational field. Why opposite? If I ask you to draw the gravitational field arrow at Earth, it's going to be like this towards the Earth, pointing towards the Earth, correct? Because remember, gravitational field always points towards the center of the body. On the other hand, if I ask you to draw the gravitational field arrow for the moon, it will point towards the moon. Now look at these two arrows. Aren't they in the opposite directions? For the Earth, it's towards the left, and for the moon, it's towards the right. And whenever vectors are in opposite directions, you have to take, in vector quantities, you have to be super careful about directions. So we have to take one of them as positive and one of them as negative. So I took the the Earth's field as positive and the moon's field as negative. It's up to you. You could do it the other way around as well. Also, one more important point to notice is notice the curve for the Earth is greater and the curve for the moon is smaller. It's because the gravity of Earth is greater and the gravity of moon is smaller. That's why. So these are very minute details that you need to take into account while drawing this graph.
If we just if we take different vectors, like if you take the moon as positive,
Yeah,
the graph is just going to be inverse, right?
definitely. It's going to be something like this. Let me maybe draw it over here. You said you want to take the moons as positive. Okay, this is moon. And then this is Earth. Notice what's the difference? The moon's is smaller and the Earth's is greater. You can absolutely do that. Yep. Okay. Now let's revise again. What are some important points to take care of while drawing this graph? Number one, make sure that they are in different quadrants. For example, one is positive, one is negative. Oh, and also this can come as a question. Actually, I remember it did come as a past paper question. You were asked that the question was something like, why are they in different parts of the graph? Why are the two graphs in the opposite quadrants? So your answer is, it is because gravitational field strength is a vector quantity. And the gravitational field directions for the Earth and Moon are opposite in direction. Please mention that it is a vector quantity. And since Moon and Earth are in opposite directions, that's why we had to take one as positive, one as negative. Okay, these are reasons. All these explanations that I'm giving you, you could be asked the reasons behind it, and you have to reason questions. Give reasoning to your solutions. Okay, number one is this. You need to take care of quadrants. Okay, one is positive, one is negative. Number two, one of the body will have a greater gravitational field value, one of them will have a smaller value. So the one that has a greater value will have a greater curve. You need to take care of that as well. Okay, and in case you get both bodies with the same gravitational field, then their curve length should be same. Just look at this. For example, I started at 9.81 over here, and for the moon, you might end at maybe 1 point something I don't exactly remember, but maybe the gravitational field of moon is something around this. Okay. This was point number 2. You need to take care of the magnitude of the gravitational field strengths. What else? Number 3, this point, the point where you are touching the x-axis. I didn't tell you yet. This point is called the null point. Meaning, at this point, the resultant gravitational field is 0. What does resultant mean? Resultant means the combination of both of them, right? Now, I just told you that both of them, both of the Earth and Moon have opposite directions of gravitational field strength. So if I want to find the resultant, should I add their field strengths or subtract? I should subtract because they are in opposite directions, right? That gravitational field of Earth minus the gravitational field of Moon. If I subtract them at any particular point, I will get the resultant gravitational field. Now, I told you at some point they will have the same gravitational fields. Now, imagine if Earth and Moon have same values. For example, Earth is also 6, let's say, and Moon's value is also 6. 6 minus 6 is 0. So, null point is a point where the resultant gravitational field strength is 0, or you could also say that the gravitational field of Earth and Moon are equal to each other. What is null point? Null point is a point where the resultant gravitational field is 0, or you could say it's where the Earth and Moon have equal field strengths. One more important point. The null point is always going to be near the smaller mass. Notice in this graph, the null point is closer to the moon. Do you see? It's not at the center of the graph. It's closer to the moon. So the null point is always going to be closer to the object with the smaller mass. Oh, and what if both the objects have the same mass? Then in that case, the null point will be at the center. Got it? These were some very important details about this graph. This graph I've seen has come as a past paper question. You were asked to completely draw the graph, and it was a 3-mark question. Or you could be asked to write some characteristics about the graph. The question in A levels can come in any possible way. You can never predict how a question can come. They always twist questions, but it's always the same concept, one way or another. It's just asked in one way or another. So this was a very, very detailed description, explanation on this graph. Now let's do another example question. How to mathematically obtain the position of the null point. This has come in past paper questions where you were given, for example, you are given two objects. Again, this is Earth and this is Moon. Okay. The null point is somewhere over here. Let's say at point X. This is the null point. You are supposed to find the distance of the null point, D, from the Earth. D, question mark. This is what you need to find. The question is, I'm repeating, the distance, find the distance of the null point from the Earth. This was the question. Okay. Now, what is given in the question? You are given the total distance between the Earth and the Moon, which is 50 RE. What is RE? RE is the radius of the Earth. They have just given you the distance in terms of the radius of the Earth. Okay, they might give you the actual distance in meters or kilometers, or they could give it to you in terms of a variable. All right. Now that's it. This is the only information given. Now, if the total distance is this, and D is what I'm finding, then can I say the distance of the moon from the null point is 50 RE minus D, right?
Right.
Now let's move on towards the solution. You're going to start with the null point. At the null point, gravitational field of Earth and Moon are equal to each other. We know this. Let us substitute the formula for the gravitational field, which is this one, gm upon r squared. Now for Earth, the distance is d. The distance between the null point and the Earth is what? It's d, according to the diagram. And the distance of the null point from the moon is 50 RE minus D whole square. Just equate them. Just equate them. Simplify, simplify, GG cancel out. You can bring the masses on both sides. The masses will be given to you. And that's it. You can solve and find D mathematically. This is how you can calculate the value, the distance of null point from a given point. Very simple. Just start with this, that at the null point, the fields are the same. Substitute the respective formulas and then just go on mathematical. The next step is mathematical. Please practice this sort of question. Or maybe just this example. You can actually practice this example after your class, just so you know that where you stand mathematically. Because I've seen a lot of students getting confused at the step. Like I've seen students who were a little not so good at maths. They found a little problem over here in simplifying. So please do this after class just to see if you're able to do the mathematical part. Okay, so right. So what are we done with so far? Gravitational field basics, formula, Newton's law, and two very important graphs. Hmm. Okay, let's see if I have a question. Okay, let's do a little question.
Miss, can you share these notes as well with us?
Yeah, sure, I will. Actually, I'm going to also send you a question that I want you guys to attempt on your own. Let me show you the question and maybe explain it roughly. And I'll send the PDF of the question in the group right now. Please attempt this question on your own anytime, but before tomorrow's class. This is the question. Define. See, this is a graph. This is a graph of gravitational field versus distance. How is the graph supposed to look like? A simple inverse square graph, because this is for an isolated star. Notice in this case, the x-axis is already starting from the surface of the star. So you can directly start from the x-axis. I mean, you don't have to make it zero. Take care of these details. Next, you are given C. This is the exact same question as I showed you right now from the notes. This is Earth, this is Moon. The distance between them is given in terms of RE. And then somewhere over here, see, you are so asked to find the distance in terms of RE from the center of the Earth at which the gravitational field strength is zero. Meaning they're talking about the null point. Oh, one more thing. In exam questions, if you are explaining something where you're talking about the null point, don't just use the word null point, because examiners will not give you marks on this word. You need to explain what null point is. Meaning you either have to say that the point where the resultant gravitational field strength is 0, or you can say a point where the gravitational field of the moon and earth are equal. Okay, do not just use the word null point, because that's just something not clear. Examiners want an explanation. So do not just use the word null point. Also, you might not even see the word null point in any question, any past paper question. This is just for your understanding, just so you remember that, okay, there was a point called null point. So anyway, see, this is the exact same question I showed you in the notes. It's for 3 marks. So try attempting this. And then in the next part, you have a graph. This is a graph that I just explained you very thoroughly over here, this one. So I want you guys to please attempt this question. However you can, if you have a tablet where you can annotate, because it's a drawing question, right? Or if you want, you can print it out and solve it, whatever is convenient for you. All right, so I'll send you this question. The video lecture will be uploaded by tonight, inshallah. And that is it. So we'll continue with gravitation tomorrow, inshallah. All
Thank you,
right.
Mr. Lafis.
Thank you, Lafis.